Hello and welcome to After Intuition. So today we will be finally proving Sine Law. To do so, we will be relying heavily on these two properties: the three unique non-collinear points defining a circle, and the angle of the center theorem. So if you want to have the proofs for those, they're in these two videos, so feel free to check them out. But perhaps as a small summary, because this one is pretty straightforward. You got 3 points that don't form a line and that don't overlap. They'll define a circle. Here you got 2 theta. Angle at the center is double the angle at the circumference, so long as the point is like there. So theta into theta. Cool. Okay. So from this angle at the center theorem, we have these different configurations. So let's connect A and B. So I'm gonna draw a line between them, and would you look at that? We got triangles now. Okay. We got triangle ABC, and we have triangles with some constant angle and some constant side length, opposing side length C. We can get C using just some trigonometry. 2r sine theta, because it's theta. And yeah, so as long as we have the same theta and we have the same r, C is going to be constant in all these cases. We don't change our r, neither our theta. So that brings the question: are all triangles with angle theta and opposing length C contained in this circle? Because we sure do have we have 3 examples of them here. So do all of them happen to be between, or have a point C between here and here? Are all those triangles formed by having the point on the circumference? The answer is a resounding yes. And why is that? Well, that's gonna go back to our first property here. 3 points, or 3 unique non-collinear points define a circle. Because 3 unique non-collinear points also define a triangle. So from that, from here, we get circle and we get triangle. And so, because that's all the information, the 3 points is all the information. Oh, can't spell. It's all the information you need to form both a triangle and a circle. For every triangle you draw, you will be able to attach it to a circle. And putting this triangle in a circle, we find this relationship. We find that the angle formed the circumference is half the angle formed at the center. And given our value of C, we have a set value for our radius. So it's going to go back in the same circle. We're going to have the same radius so that we can have our same C, because theta is the same theta. Cool. So how about we just toggle that triangle a bit? Let's move point C until angle A is 90 degrees. And just before we proceed, let's just let theta for now be less than 90 degrees. So we can form a 90-degree triangle with angle theta. And because that triangle exists and it has side length C opposing it, it will fit in the same circle. So we're just moving point C along the circumference. Okay. So some observations. Hypotenuse CB is the diameter. Why? Recall the angle of the center theorem video. That's kind of why I had the extra proportion there. Pretty much, if you're gonna have a 90-degree triangle inscribed in a circle, you're gonna have 180 degrees of 180-degree angle formed at the center. And so it's gonna run, you're gonna have this line now running straight through the circle. Is going to be our diameter. So yeah, so here hypotenuse CB still is our diameter. So let's take this and solve for our diameter here, or solve for 2r, which is diameter. Here, so we know sine theta equals C over 2r. Yeah. So we got 2r is equal to C over sine theta. Cool. So this is our diameter. Diameter. Okay. Which already looks suspicious, but before we keep going, is this conversation even relevant? Right? Because like theta could be greater than 90, so we can't form a 90-degree triangle. For that, I'm gonna let's refer to this animation just to give us some sort of basis. And welcome back. So from our animation, we saw how the point of view changes, because you know how before I was saying, yes, like you have to be on this side for this to be true. That's because we have a change in perspective of what our center angle is. So when we're here, or when both angles are pointed, let's call it upwards, this 2 theta here gets translated to a theta here. But when both angles, let's say they're pointing downward, like increasing in this direction, the center angle is actually going to be this one. So this comes 180 minus theta. And while this angle is changing, it's become the theta and 180 minus theta, they're supplementary angles. The side length here does not change, so just make note of that. C does not change because ultimately the placement of these lines is the same on the circle. They're still 2 theta apart, or 2 theta minus 360 apart. Ultimately, same placement on the circle. So, we know C does not change. Now just maybe as a little refresher about what sine's doing. Sine refresh. So, when theta is less than 90, you're taking opposite over hypotenuse. That's what sine's doing, right? Sine is opposite over hypotenuse. But then when sine becomes greater than 90, we're not really taking like some sort of opposite side here. Instead, we're looking at the height of the triangle formed. So perhaps it's just better in general to say it's height. But oh well. So height over hypotenuse, which in this case is the radius. Hypotenuse. So that's why it's different. So because with supplementary angles, when you have the 180 minus theta, or when you have just the theta, you have the same height. When you do this ratio above, you're gonna get the same value because sine theta is giving you the height of here. Oh, paste. Oh, where's the option? Okay, so for this, ultimately you're gonna get the same value. I think you know. Oh, beautiful. Okay, so because this value stays the same and this value stays the same. But if you want to imagine it like in the actual circle, you can think of it this way, where you have our angle and then the height or the height of the opposing side, the height or the length of the side that is perpendicular to it is C. And because we have this perpendicular thing, hypotenuse is going to be our diameter. So you could think of it this way, or you could think, okay, well, this sine theta is the same value, so it's whatever. So one way, second way to think about it. But yeah, so we can then ask, what if theta is 90 degrees? If theta is 90 degrees, it's really the case that we had up here. Pasted here. So C would then just be our diameter. So C, C equals to R. And also sine of 90, because in this case theta is 90. Then 90 equals 1. So when we do C over sine of 90, we're just going to get C, which we know is equal to 2R. So it is equal to diameter. But yeah, this is more of like a little tangent. But anyway, so knowing what we know, we can actually expand sine law. Because we know that all this ratio is doing is it's giving us the diameter of the circle that the triangle is inscribed in. So we have this green triangle. What's the diameter of the circle that this green triangle is inscribed in? It's D over sine of D, which is also equal to E over sine of E, which is also equal to F over sine of F. Why? Well, in all of our exploration, we didn't actually specify like, oh, this has to be angle to the left or whatever. All of our arguments apply to every single angle on the triangle, so all 3 angles, okay? So yeah, so we can equate this together. We're gonna get the 2R in all cases. And then also for our like gold triangle, we have the same thing. So A over sine of A equals B over sine of B equals C over sine of C equals 2R. So ultimately we can equate these all together. As long as a triangle belongs to that circle, you can draw this equality. And yeah, so this is our sine law, or even our expanded sine law. Recall above, this is a little tangent, but recall above how we also said that C equals 2R sine theta. So we could have also really derived sine law from this, but visually this looks so much more pretty. So yeah, just maybe some homework for you would be to prove it like the other way, just by looking at this center angle. But yeah, that's all. Thank you so much for your patience and for hanging with me in this like 3-part series. It was a pleasure. I'll see you guys next time. Bye.